Hello everyone, and welcome back to our channel. We often think of scientific history as a clean timeline of famous names and breakthrough moments. But many of the most crucial discoveries were made by brilliant minds who have been lost to time. Today, we're telling the story of one such pioneer, Nettie Stevens. In the early 1900s, she solved one of biology's greatest mysteries, how sex is determined, by discovering the X and Y chromosomes. Yet, her name is rarely mentioned in the same breath as this monumental achievement. This is the story of her discovery and why her legacy deserves to be remembered. To grasp the scale of her breakthrough, we must understand the scientific landscape she navigated. At the turn of the 20th century, genetics was a fledgling science. Mendel's laws of heredity had just been rediscovered, but the physical basis for these laws was unknown. The gene was a purely abstract concept. The question of sex determination was a major puzzle, and the leading theory was that the environment was the deciding factor. Scientists seriously proposed that things like nutrition or temperature could determine whether an embryo developed as male or female. This meant there was no universal biological mechanism. It was into this confusing and speculative arena that Nettie Stevens brought her methodical and empirical approach, seeking a concrete physical answer within the cell itself. Nettie Stevens' own journey was one of incredible perseverance. She did not follow a traditional academic path. She worked for years as a teacher, saving money to fund her own higher education. She enrolled at Stanford University at age 35 and didn't complete her PhD at Bryn Mawr College until she was 41. In an era when science was overwhelmingly male-dominated, her dedication to pursuing research was remarkable. After her doctorate, she focused on cytology, the study of cells, and the emerging questions of heredity. She chose the mealworm as her research subject. This was a strategic choice. The insect was easy to breed, and its cells contained a small number of large, easily observable chromosomes. Her work was the epitome of meticulous, painstaking labor. It involved countless hours spent preparing slides and peering through a microscope, staining cells to reveal their internal structures, and methodically documenting what she saw. She wasn't just observing, she was comparing, looking for a consistent difference between the cells of males and females. Her relentless search paid off. Stevens discovered an unambiguous physical difference. In the somatic cells of female mealworms, she consistently counted 20 large chromosomes. In the cells of males, however, she found 19 large chromosomes and one distinctly small one. This was the critical evidence. The difference was not external or random, it was an inherent chromosomal distinction. In her groundbreaking 1905 paper, she laid out her findings with exceptional clarity. She concluded that the female was XX, possessing 2 large sex chromosomes, while the male was XY, possessing 1 large and 1 small sex chromosome. She correctly deduced that the sperm cell determined the sex of the offspring. If it carried an X, the result was a female. If it carried a Y, the result was a male. This was not a tentative suggestion, it was a confident declaration of a fundamental biological mechanism. The significance of this discovery was immense. It provided the first concrete evidence linking a specific inherited trait, sex, to a specific chromosome, thereby becoming a cornerstone of the chromosome theory of inheritance. It transformed the abstract concept of heredity into something tangible and observable. Unfortunately, Stevens' recognition was immediately complicated. Edmund Beecher Wilson, a more prominent researcher at Columbia University, published similar findings around the same time. Though Stevens' paper was arguably clearer and more definitive in its conclusion, Wilson's established reputation often led to him receiving the lion's share of the credit. Furthermore, her former mentor, Thomas Hunt Morgan, who would later win a Nobel Prize for his work on fruit fly genetics, was initially a skeptic of her theory. Even after his own work validated her discovery, he tended to minimize her specific contribution in his writings and lectures, a classic example of the Matilda effect, where the work of female scientists is overshadowed by their male colleagues. Stevens's premature death from cancer in 1912, just 7 years after her discovery, left her unable to advocate for her own legacy. Bringing Nettie Stevens' name to the forefront is more than just a historical correction. It's a vital reminder that scientific progress is often driven by the quiet, persistent work of individuals who overcome immense barriers. Her story challenges the great man narrative of science and reveals a more complex and ultimately more inspiring truth about how discovery happens. It is our generation that must ensure her foundational contribution to genetics is not just a footnote, but a headline. What do you think is the best way to ensure forgotten figures in science get the recognition they deserve? Let us know your thoughts in the comments. Subscribe for more untold stories, and we'll see you in the next one.